Hello and welcome to the next video in the Crafting Interpreters series. In this series we are going to read the book Crafting Interpreters by Robert Nystrom, and we are going to write an interpreter of a LOX language using Go. Now in the previous video we are basically just reading the introduction, so hopefully in this installment we can finally start writing some code. But first let me just finish the introduction part of the book. So yesterday we discussed the formal grammar of a language. There are function calls, and we have discussed things like control flow, variable declarations, print statements. Then there are functions, and functions are defined with the word fun, and also they are called the same as in C or in JavaScript. And also if you pass a function without parentheses, it will just pass a function reference and will not call the function, unlike languages like Ruby or I think Elixir also. And then, yes, this section also discussed the difference between an argument and a parameter. And an argument is the actual thing you pass to a function, and a parameter is a formal definition of what is used in the declaration and not in the definition of the function. Then LOX will have closures, which we will not implement until the very end of the first part of the book. And closures are basically an idea that you can have a locally defined function, and that function is going to maintain a copy of the scope of the parent function. Okay, so I'm just going to skim over all of this because I don't think most of my viewers want to hear me read the definition part. Then in section 3.9 we have classes, and maybe I'm going to read this part. Since LOX has dynamic typing, lexical, roughly block scope, and closures, it's about halfway to being a functional language. But as you'll see, it's also about halfway to being an object-oriented language. Both paradigms have a lot going for them, so I thought it was worth covering some of each. Since classes have come under fire for not living up to their hype, let me first explain why I put them into LOX and this book. There are really two questions. Why might any language want to be object-oriented? Now that object-oriented languages like Java have sold out and only play arena shows, it's not cool to like them anymore. Why would anyone make a new language with objects? Isn't that like releasing music on 8-track? It is true that all inheritance all the time binge of the 1990s produced some monstrous class hierarchies, but object-oriented programming is still pretty rad. Billions of lines of successful code have been written in OOP languages, shipping millions of apps to happy users. Likely, a majority of working programmers today are using an object-oriented language. They can't all be that wrong. In particular, for a dynamically typed language, objects are pretty handy. We need some way of defining compound data types to bundle blobs of stuff together. If we can also hang methods of those, then we avoid having the need to prefix all of our functions with the name of the data type they operate on to avoid colliding with similar functions for different types. In, say, Racket, you end up having to name your functions like hash copy to copy a hash table and vector copy to copy a vector, so that they don't step on each other. Methods are scoped to the object, so that problem goes away. I could claim objects are groovy, but still out of scope for the book. Most programming language books, especially ones that try to implement a whole language, leave objects out. To me, that means the topic isn't well covered. With such a widespread paradigm, the omission makes me sad. Given how many of us spend all day using OOP languages, it seems like the world could use a little documentation on how to make one. As you'll see, it turns out to be pretty interesting. Not as hard as you might fear, but not as simple as you might presume either. Classes or prototypes. When it comes to objects, there are usually two approaches to them: classes and prototypes. Classes came first and are more common thanks to C++, Java, C#, and Friends. Prototypes were a virtually forgotten offshoot until JavaScript accidentally took over the world. In class-based languages, there are two core concepts: instances and classes. Instances store the state for each object and have a reference to the instance's class. Classes contain the methods and inheritance chain. To call a method on an instance, there is always a level of indirection. You look up the instance's class and then you find the method there. So in this example, the Eggs Benedict is an instance of branch, and it inherits from breakfast. Side note: in a statically typed language like C++, method lookup typically happens at compile time based on the static type of the instance, giving you static dispatch. In contrast, dynamic dispatch looks up the class of the actual instance object at runtime. This is how virtual methods in statically typed languages and all methods in a dynamically typed language like locks work. Prototype-based languages merge these two concepts. There are only objects, no classes, and each individual object may contain state and methods. Objects can directly inherit from each other, or delegate to in prototypal lingo. Side note: in practice, the line between class-based and prototype-based languages blurs. JavaScript's constructor function notion pushes you pretty hard towards defining class-like objects. Meanwhile, class-based Ruby is perfectly happy to let you attach methods to individual instances. Okay, so this is a diagram of a prototype-based approach. In this example, this is called classy branch. It's not actually a class. The classy branch is an object with the property of bread and a method of drink, and then the for some reason the some of the methods or properties are delegated to a prototype chain. This means that in some ways prototypal languages are more fundamental than classes. They are really neat to implement because they are so simple. Also, they can express lots of unusual patterns that classes steer away from. But I've looked at a lot of code written in prototypal languages, including some of my own devising. Okay, I'm going to click this link. Okay, so it's a language. Okay. Do you know what people generally do with all the power and flexibility of prototypes? They use them to reinvent classes. I don't know why that is, but people naturally seem to prefer a class-based, classic, classy style. Prototypes are simpler in the language, but they seem to accomplish that only by pushing the complexity onto the user. So for locks, we'll save our users the trouble and bake classes right in. Side note, Larry Wall, Perl's inventor prophet, calls this the waterbed theory. Some complexity is essential and cannot be eliminated. If you push it down in one place, it swells up in another. Prototypal languages don't so much eliminate the complexity of classes as they do make the user take that complexity by building their own class-like metaprogramming libraries. Classes in locks. Enough rationale. Let's see what we actually have. Classes encompass a constellation of features in most languages. For locks, I've selected what I think are the brightest stars. You declare a class and its methods like so. Class breakfast, method cook, print eggs are frying, serve, this takes a parameter called who, print enjoy your breakfast, who. The body of a class contains its methods. They look like function declarations, but without the fun keyword. When the class declaration is executed, locks creates a class object and stores that in a variable named after the class. Just like functions, classes are first class in locks. Side note, they're still just as fun though. This is in the relation of the missing fun keyword. Okay, so this shows that you can store a class in a variable and you can pass it to a function. Next, we need a way to create instances. We could add some sort of new keyword, but to keep things simple, in locks, the class itself is a factory function for instances. Call a class like a function and it produces a new instance of itself. Var breakfast equals breakfast called as a function. Print breakfast, breakfast instance. Instantiation and initialization. Classes that only have behavior aren't super useful. The idea behind object-oriented programming is encapsulating behavior and state together. To do that, you need fields. Locks, like other dynamically typed languages, lets you freely add properties onto objects. Breakfast.meat equals sausage, breakfast.bread equals sourdough. Assigning to a field creates it if it doesn't already exist. If you want to access a field or method on the current object from within a method, you use good old this. Okay. Part of encapsulating data within an object is ensuring the object is in a valid state when it's created. To do that, you can define an initializer. If your class has a method named init, it is called automatically when the object is constructed. Any parameters passed to the class are forwarded to its initializer. Inheritance. Every object-oriented language lets you not only define methods, but reuse them across multiple classes or objects. For that, locks supports single inheritance. When you declare a class, you can specify a class that it inherits from using a less than operator. Side note, why the less than operator? I didn't feel like introducing a new keyword like extends. Locks doesn't use colon for anything else, so I didn't want to reserve that either. Instead, I took a page from Ruby and used less than. If you know any type theory, you'll notice it's not a totally arbitrary choice. Every instance of a subclass is an instance of its superclass too, but there may be instances of the superclass that are not instances of the subclass. That means In the universe of objects, this set of subclass objects is smaller than the superclasses set, though type nerds usually use a less than colon for that relation. Here, branch is the derived class or subclass, and breakfast is the base class or superclass. Every method defined in this superclass is also available to its subclasses. For Benedict equals branch with ham and English muffin, and benedict.serve noble reader will print a method just like if it were called on the breakfast, on an instance of breakfast. Side note, logs is different from C++, Java, and C#, which do not inherit constructors, but similar to Smalltalk and Ruby, which do. Even the init method gets inherited. In practice, the subclass usually wants to define its own init method too. But the original one also needs to be called so that the superclass can maintain its state. We need some way to call a method on our own instance without hitting our own methods. As in Java, you can use super for that. That's about it for object orientation. I tried to keep the feature set minimal. The structure of the book did force one compromise. Logs is not a pure object-oriented language. In a true object-oriented language, every object is an instance of a class, even primitive values like numbers and booleans. Because we don't implement classes until well after we start working with the built-in types, that would have been hard. So values of primitive types aren't real objects in the sense of being instances of classes. They don't have methods or properties. If I were trying to make logs a real language for real users, I would fix that. Okay. Now, I'm going to skim over this section. This basically says that the only functions implemented in the standard library are going to be print, which is actually a statement and not a function, and clock. And this is because we want to track the current time. And this is everything we are going to implement in terms of a standard library in this book. We can do whatever we want besides that, but print and clock is all that is defined in this book. If you wanted to turn logs into an actual useful language, the very first thing you should do is flesh this out. String manipulation, trigonometric functions, file I/O, networking, heck, even reading input from the user would help. But we don't need any of that for this book, and adding it wouldn't teach you anything interesting, so I left it out. Don't worry, we'll have plenty of exciting stuff in the language itself to keep us busy. Okay, there are challenges, but these are not related to. They are not related to the. They're not related to the actual code we're going to write. So I'm going to skip the challenges. And this is a side note, but I think this is also hair splitting. So I am going to go to the next part. And after a quick break for water. Okay, so in this part, now begins the part 2 of the book, in which we are going to write a tree-walk interpreter. And this section is basically an introduction. And I'm just going to skip over it and go to the next chapter. in which we are going to write a lexer or a scanner. Quote, take big bites, anything worth doing is worth overdoing. Robert A. Heinlein, Time Enough for Love. The first step in any compiler or interpreter is scanning. The scanner takes in raw source code as a series of characters and groups it into a series of chunks we call tokens. These are the meaningful words and punctuation that make up the language's grammar. Side note, this task has been variously called scanning and lexing, short for lexical analysis, over the years. Way back when computers were as big as Winnebagos, but had less memory than your watch, some people used scanner only to refer to the piece of code that dealt with reading raw source code, characters from disk, and buffering them in memory. Then lexing was the subsequent phase that did useful stuff with the characters. First, what's Winnebagos? Okay, so a Winnebago is apparently a type of an RV. Perfect for cooking crystal meth, right? These days, reading a source file into memory is trivial, so it's rarely a distinct phase in the compiler. Because of that, the two terms are basically interchangeable. Scanning is a good starting point for us too, because the code isn't very hard, pretty much a switch statement with delusions of grandeur. It will help us warm up before we tackle some of the more interesting material later. By the end of this chapter, we'll have a full-featured, fast scanner that can take any string of log source code and produce the tokens that will fit into the parser in the next chapter. The interpreter framework. Since this is our first real chapter, before we get to actually scanning some code, we need to sketch up the basic shape of our interpreter JLogs. Everything starts with a class in Java. So, I'm going to open a new Go project. mkdir go logs. And initialize a new Go project. I'm going to set up a Go version, and I'm going to initialize a repository. And then I'm going to initialize a JJ repository because this is what I usually use instead of Git. Okay, great. And now in main.go, you can do a similar thing to what they did here. So let's say func main if length of osargs is greater than 1, fmt println usage go logs script os exit 64. If length of osargs equals 1, also I don't think this is going to work like this because osargs also contains the program name, so this has to be 2. and if this is like this, then we run file args os.args at 1 and else run prompt. Okay, none of this is going to compile for now. For exit codes, I'm using the conventions defined in the Unix sysexits header. It's the closest thing to a standard I could find. And this is from FreeBSD. Stick that in a text file and go get your IDE or makefile or whatever setup. I'll be right here when you're ready. Good, okay. Now this references the fact that the book does not instruct you how to build the code, because such instructions would take a lot of space and would very quickly get outdated. LOX is a scripting language, which means it executes directly from source. Our interpreter supports two ways of running code. If you start JLOX from the command line and give it a path to a file, it reads the file and executes it. Private static void run file string path throws IO exception. Func run file path string and error, and then bytes error equals os read file path. If error is not nil, return nil, and then run string bytes. Okay. Also, I guess we could define these as methods on a class. So type LOX struct, and then this would be I guess this would be a method on the LOX type, and this should probably also be I'm going to initialize a LOX instance in here, and this is going to be a method, and this is going to be a method as well. Okay. If you want a more intimate conversation with your interpreter, you can also run it interactively. Fire up JLOX without any arguments, and it drops you into a prompt where you can enter and execute code one line at a time. An interactive prompt is also called a REPL. The name comes from Lisp, where implementing one is as simple as wrapping a loop around a few built-in functions. Working outwards from the most nested call, you read a line of input, evaluate it, print the result, then loop and do it all over again. Now the next method, func LOX run prompt, and this returns an error. So input stream reader input. New input stream reader. I think this can be implemented as a wait, what does it say? Oh, I guess this. Is it something like byte writer, or buff.io? New scanner, I guess. I'm not exactly sure. New scanner OS std in, and for fmt print a prompt line equals input scan. Was it? Okay, I'm going to open up the documentation quickly. What did they call here? Buff.io scanner. Scanner provides a convenient interface for reading data such as file or new line delimited lines of text. Successive calls to the scanner.scan method will step through the tokens of a file, skipping the bytes between the tokens. The specification of a token is defined by a split function of type splitfunc. The default split function breaks the input lines with line termination into lines with line termination stripped. Scanner.split functions are defined in this package for scanning a file into lines, bytes, UTF-8 encoded runes, and space delimited words. The client may instead provide a custom split function. Scanning stops unrecoverably at end of file with first IO error or a token too large to fit in the scanner.buffer. Okay. Okay, so I guess this is what's going to happen. So we get the next line, which would be input text, like so, I guess. And then we run the line, like so. This is still not going to compile, so I'm not sure if this is the correct way to do it. Working outwards, okay, yes, so we define a run prompt function. The readline function, as the name so helpfully implies, reads a line of output from the user on the command line and returns the result. To kill an interactive command line app, you usually tap Ctrl-D. Doing so signals an end of file condition to the program. When that happens, readline returns null, so we check for that to exit the loop. Both the prompt and the file runner are thin wrappers around this core function. Private static void run string source. Okay, so func logs run source, which is a string. And then we have to initialize a scanner, which is going to be even more. Yeah, I'm guessing this scanner will live in a different package. Yeah, I'm going to omit this for now. Well, source and tokens equals scanner scan tokens, and for token in the range of tokens fmt printf println token. Okay, and okay, and this doesn't really return an error here. Yeah, we'll see to the error handling later on. The readline function, as the name so helpfully implies. Okay. It's not super useful yet since we haven't written the interpreter, but baby steps, you know. Right now it prints out the tokens our forthcoming scanner will emit, so that we can see if we're making progress. Error handling. While we're setting things up, another key piece of infrastructure is error handling. Textbooks sometimes gloss over this because it's a practical matter than a formal computer sciencey problem. But if you care about making a language that's actually usable, then handling errors gracefully is vital. The tools our language provides for dealing with errors make up a large portion of its user interface. When the user's code is working, they aren't thinking about our language at all. Their headspace is all about their program. It's usually only when things go wrong that they notice our implementation. When that happens, it's up to us to give the user all the information they need to understand what went wrong and guide them gently back to where they are trying to go. Doing that well means thinking about error handling all through the implementation of our interpreter, starting now. Having said all that, for this interpreter, what we'll build is pretty bare bones. I love to talk about interactive debuggers, static analyzers, and other fun stuff, but there is only so much ink in the pen. Okay, so func l logs error. I cannot use this. I can't use this name for a method. Line integer and message string, and L report line message func L logs report line integer where msg string fmt println printf actually a line number error string and message, new line. Okay, this is line where message, and then head error would be true, and this means that we have to define a head error field on the struct. Like so. This error function and its report helper tells the user some syntax error occurred on a given line. That is really the bare minimum to be able to claim you even have error reporting. Imagine if you accidentally left a dangling comma in some function call and the interpreter printed out error unexpected comma somewhere in your code. Good luck finding it. That's not very helpful. We need to at least point them to the right line. Even better would be the beginning and end column so we know where in the line. Even better than that is to show the user the offending line like so. I love to implement something like this in this book, but the honest truth is that it's a lot of grungy string manipulation code. Very useful for users, but not super fun to read in a book and not very technically interesting. So we'll stick with just a line number. In your own interpreters, please do as I say and not as I do. The primary reason we're sticking this reporting function in the main logs class is because of that head error field. It's defined here. We'll use this to ensure we don't try to execute code that has a known error. Also, it lets us exit with a non-zero exit code like a good command line citizen should. Okay, so in run file, if there was if L had error, then OS exit 65. We need to reset this flag in the interactive loop. If the user makes a mistake, it shouldn't kill their entire session. Okay, so L head error equals false. The other reason I pulled the error reporting out here instead of stuffing it into the scanner and other phases where the error might occur is to remind you that it's good engineering practice to separate the code that generates the errors from the code that reports them. Various phases of the frontend will detect errors, but it's not really their job to know how to present that to a user. In a full featured language implementation, you will likely have multiple ways errors get displayed. On standard error, in an IDE's error window, log to a file, etc. You don't want the code smeared all over your scanner and parser. Ideally, we would have an actual abstraction, some kind of error reporter interface that gets passed to the scanner and parser so that we can swap out different reporting strategies. For our simple interpreter here, I didn't do that, but I did at least move the code for error reporting into a different class. I had exactly that when I first implemented JLogs. I ended up tearing it out because it felt over-engineered for the minimal interpreter in this book. With some rudimentary error handling in place, our application shell is ready. Once we have a scanner class with a scan tokens method, we can start running it. Before we get to that, let's get more precise about what tokens are. Lexemes and tokens. Here is a line of logs code. var language equals string logs. here, var is the keyword for declaring a variable, but three character sequence var means something. But if we yank three letters out of the middle of language, like GUA, these don't mean anything on their own. That's what lexical analysis is about. Our job is to scan through the list of characters and group them together into the smallest sequences but still represent something. Each of these blobs of characters is called a lexeme. In that example line of code, the lexemes are var language equals logs. The lexemes are only the row substrings of the source code. However, in the process of grouping character sequences into lexemes, we also stumble upon some other useful information. When we take the lexeme and bundle it together with that other data, the result is a token. It includes useful stuff like token type, keywords are part of the shape of a language's grammar, so the parser often has code like if the next token is while, then do. That means the parser wants to know not just that it has a lexeme for some identifier, but that it has a reserved word and which keyword it is. The parser could categorize tokens from the row lexeme by comparing the strings, but that's slow and kind of ugly. Instead, at the point that we recognize a lexeme, we also remember which kind of lexeme it represents. We have a different type for each keyword, operator, bit of punctuation, and literal type. After all, string comparison ends up looking at individual characters. And isn't that the scanner's job? Okay, so we're going to define a new file. And for now, I'm just going to leave it in the same package, and then we will see. Package main for now, and then type token type int in const token type, and then left paren. Yeah, so I think we're going to have to prepend these with the token type thing. Otherwise, we're going to have to otherwise this is going to cause confusion. So anyway, I'm going to replace these commas with new lines, and then I'm going to prefix each of those with a text token type. No, wait, first I'm going to convert all of these to Pascal case. Wait, yeah. So norm, like so. Then this is okay. Token type equals iota, like so. Okay. And now we can prepend each of those with the with the name token type. Like so. This is the way enums are usually implemented in Go. And we are doing something similar for these. First, we replace new lines with we replace commas with new lines, then we make them Pascal case, and then we prepend token type. Great. And then literals. Great. And then keywords. And finally, token type end of file. And I'm going to leave this in all caps. Okay, great. So we have defined the token type enum. And let's go. Literal value. There are lexemes for literal values, numbers and strings and the like. Since the scanner has to walk each character in the literal to correctly identify it, you can also convert the textual representation of a value to the living runtime object that will be used by the interpreter later. Okay, yes, so this means that the token will also need to contain a literal value. Also, when I interpreted this in Rust, I actually used a Rust enum. And as you know, Rust enums can have different fields depending on the variant of this enum. So in like Rust logs, I think in token, I had this token type, and so like literals had a string attached to them, and strings had strings attached to them, and numbers were float 64s, and everything else was just a plain variant of this enum. And now that I think of it, it may have been a bit wasteful, because this also means that for every simple token we need to assign, we need to allocate memory for like a string. But hey, it was a fun project. Location information. Back when I was preaching the gospel about error handling, we saw that we need to tell users where errors occurred. Tracking that starts here. In our simple interpreter, we note only which line the token appears on, but more sophisticated implementations include the colon and length too. Some token implementations store the location as 2 numbers, the offset from the beginning of the source file to the beginning of a lexeme, and the length of a lexeme. The scanner needs to know this anyway, so there is no overhead to calculate them. An offset can be converted to line and column positions later by looking back at the source file and counting the preceding new lines. That sounds slow, and it is. However, you need to do it only when you need to actually display a line and column to the user. Most tokens never appear in an error message. For those, the less time you spend calculating position information ahead of time, the better. We take all of this data and wrap it in a class. And that's also a new file. Okay. A token go. Type token struct, and it has a token type, which is a token type, and a lexeme, which is a string. The object okay, can I do an object thing? No, I cannot. Shit. Okay, yeah, I can just make it an any. and the line, which is going to be an integer. And then in the, I'm going to need to define an initializer, a constructor, so to say, a type, which is a token type. And also this cannot be called type. Okay, well, a lexeme, which is a string, and literal, which is any, and line, which is an integer. Return token. Okay, so I'm just going to put these like so. Lexeme, literal, line. Okay, and it has to return a token. Okay, and then func token to a string. This is actually called string because this is an implementation of stringer, I think. And return fmt sprintf type lexeme and literal. Oh yeah, and this is literal and not an object. So this is going to be a v instead. And also for token type, we are going to need to define a representation thing. So I think we're going to have to install stringer. And so go in get to this, go install to stringer. Okay, stringer type token type. Okay, what did you get? Let's see what it was. Invalid array index. Okay, I have no idea how this works, but this is generated with stringer, and I'm just going to commit it at some point. Great. The token type is an enum. This is a string. Okay, let's just hope this works. Now we have an object with enough structure to be useful for all the later phases of the interpreter. Also, wait, did we get this in the string thing? Did we get? Oh, okay. Let me see if we can get. Can we somehow get? Wait, can we get this? Can we make it like this? So. Like with line comment. so that like okay, yeah, I'm going to have to do more research about this stringer thing, but it's very commonly used in the Go ecosystem. Oh yeah, no, it worked. It replaced the left parent thing with token type left parent with this left parent thing. So ideally, we should also have a way to do it for everything, but I don't think we can. Okay, now we have an object with enough structure to be useful for all of the later phases of the interpreter. Also, we have reached an 1 hour timestamp in this video, and I think this chapter is long enough that we can't really get this program running if we just keep on grinding this for like 20 minutes. So I'm going to wrap up for today. And if you have enjoyed watching this content, please consider liking and subscribing. It really means a lot to me. And you have been watching Make Programming Fun Again, and my name is Karol Moros. Thank you.